In this lecture, we will now try to apply the knowledge of elastic constants, rigidity modulus, Young's modulus, bulk modulus to a real-time application. We are going to discuss couple per unit twist in the case of cylinder, solid cylinder. What is couple per unit twist? I'll take a cylinder. See here is a cylinder. Imagine this to be a solid cylinder. This cylinder can be imagined to be made of large number of concentric cylinders of increasing radius. This is the outer part of the cylinder what you are seeing. This is imagined to be a solid cylinder. So axis is at the center, and now suppose if this is fixed here rigidly and a couple is applied here. What is a couple? Two equal and opposite forces separated by a distance. See here, I am trying to push this part this way, whereas this part is coming towards me. So I am applying a twist. This twist is experienced by any steel rod used in a pillar, a steel wire used in a bridge. Correct? So construction engineers need to know how the couple per unit twist affects the elasticity of the material. Not only in civil engineering, in mechanical engineering, in vehicle design, they experience stress couple in different situations. So this is a very important problem. Now imagine this top end is rigidly fixed, and now I am going to twist this. Here this is fixed, this is twisted. What happens to this point P? You observe the point P gets displaced to a new point. Correct? So remember, this is the shearing stress I am applying. When a shear stress is applied tangential to the surface, see the outermost outermost layer of the cylinder experiences maximum strain, displacement. See, outermost layer gets displaced like this. Correct? In the case of solid cylinders, this displacement is very less. This is made of a small cardboard, so you see so much of strain. But if you take a steel rod, steel wire and twist it, the displacement is very less. Can you recollect your experience with lab experiment called as rigidity modulus determination in physics lab? In physics lab, you have a heavy rigid body suspended by a steel wire and you apply a couple there. Because of the couple, you are setting up a torsional oscillation. So indirectly, while doing that experiment, you are actually using this elastic properties theory. Okay? So this cylinder, when you apply a couple, this gets twisted. We will now find the expression for the torque on this cylinder. Torque is couple. Okay? Determination of couple is the objective of this derivation. Now, I'll imagine this cylinder of radius x. The upper end of the cylinder is fixed. The couple is applied at the lower end. Okay? So the axis of the cylinder be this one. Let the length of the axis be L. Okay? The point P which I showed you, which is getting displaced due to the application of the couple, is, let this initial position of the point B be here. Okay? So the point B can be imagined to be in this plane. Do you see the plane here? Okay. Now due to the application of couple, correct, the point B shifts to this point B1, B prime. So this end is fixed, correct? The upper end is fixed. So therefore now point B has to be represented in this plane, correct? Do you see that? Now let the radius of this cylinder be x. Let the thickness of the cylinder be dx. So what I have written is this: the cylinder radius is x. Let the thickness be very small, dx. Thickness is dx. This is the original point. It gets displaced to this point. Okay. Now we have to find the expression for couple. Let this angle be phi. It is called as shearing strain. Let this angle be theta. Okay. Now from the diagram, see here, you can write BB prime, okay, is equal to, this is L into phi. Can you write this? See this? Imagine this triangle B, B prime and A. From triangle B, B prime A, this is A, B, B prime A, this is phi. This BB prime is equal to length L into phi. Why? Do you remember this mathematical expression? If this is S, this is R, this is theta. When theta is very small, S is equal to R into theta. Correct? So I am applying that. Now look at another expression. Let this be O. From triangle OB prime, from triangle OBB prime, what can you write? BB prime is equal to x into theta. BB prime is equal to x into theta. Okay. Now look at these two expressions. BB prime is this, BB prime is this. So from these two, I can write phi is equal to x theta by L. Correct? Shear strain. The shear strain is net displacement of the surface with respect to the stationary surface. See, this central axis will not experience any displacement, and as you move away from the center, as the radius increases, the displacement increases. The outermost layer, this cylinder, experiences maximum displacement, shear displacement. So B has moved to B prime. So now I will write the expression for shear stress. We know rigidity modulus is equal to shear stress by shear strain. It is shear stress by shear strain. Now let the shear stress be force by area. Shear strain is this x theta by L. Okay. Now rest is simplification. Now what is the area we are considering? The couple acts on this area. See here? Correct? Dx is assumed to be very small. We are applying stress on the outermost surface of thickness dx, radius x. So area of this circular ring will be 2 pi x into dx. Correct? So couple is applied on that thickness. So now because of this, I'll substitute for A. rigidity modulus is equal to F by 2 pi x into dx into x theta by L. Therefore, force, the tangential force, the shear force applied is equal to rigidity modulus into 2 pi x dx into x into theta by L. Correct? By knowing the force, we can calculate couple and moment of couple. Moment of couple is tau. Now, this is, I take out the constant 2 pi eta by L x square dx. I need couple or the moment of force. Couple is moment of force is equal to force into distance. The distance is from the center x because the central axis does not experience any displacement. The outermost layer is experiencing maximum displacement. The central axis is not experiencing any displacement. So this distance, the shear is with respect to this central axis which is not experiencing any displacement. So force into displacement. Therefore, 2 pi eta by L x cube dx. Okay. Now we will calculate the total moment. Total moment. We have to integrate this from center to the ring. So 0 to, let the radius of the cylinder be r. Let the radius be r. So we will integrate from 0 to fx dx from 0 to r. So when we integrate this, 2 pi eta by L x cube by x cube, when you integrate it, it becomes x to the power of 4 by 4 and limits are r, so it is r to the power of 4 by 4. Correct? So now the last expression is total moment, that is nothing but torque. Total moment of force is torque, tau, is equal to, see here 2, this is 2 pi rigidity modulus r4 into theta by 2L. We need couple per unit twist. So this torque is also called as couple. Now I'll take theta this side per unit twist is equal to tau by theta pi eta r4 by 2. Is it clear? So this is the expression we needed to derive. Now we extend this to torsional pendulum. See, you have done the rigidity modulus determination in torsional pendulum experiment. You are making a rigid body perform torsional oscillation. Now you can relate this expression with that experiment. We will apply this for a torsional pendulum, right? In a torsional pendulum, torsional oscillations are produced. What is torsional oscillation? Imagine a circular solid plate suspended from a rigid support. When you give a couple here, it performs simple harmonic motion. Please remember, torsional oscillations are also simple harmonic oscillations. Then what is this expression similar to simple harmonic oscillations experienced in a normal vibration? We all know in a normal vibration, the simple harmonic vibration, force is proportional to displacement. Force is m into d square x by dt square. is equal to minus kx, correct? Now you will get a similar expression with torsional pendulum also. In a torsional pendulum, torque tau is equal to moment of inertia into angular acceleration. This is the expression similar to this. Okay? So therefore, this is I into d square theta by dt square. What is angular acceleration? Rate of change of angular velocity. What is angular velocity? D theta by dt. Derivative of that is d square theta by dt square. Omega is d theta by dt. Angular acceleration is d omega by dt. That is d square theta by dt. Correct? Now this is, we have shown this torque. From this expression, we have shown that this is pi eta r4 theta by 2l. Correct? Look at this expression. Torque is equal to moment of inertia into angular acceleration. And we have also shown torque is equal to this expression. So now, I just write like this here. I into d square theta by dt square is equal to a constant c into theta. Correct? This constant is this. Correct? Now, I can write this as d square theta by dt square is equal to c by I into theta. Correct? This is similar to what? Here, look at this expression. D square x by dt square is equal to k by m into x. You understand this? See, in a normal simple harmonic motion, when an object is performing simple harmonic motion, this is the equation we use. Force is proportional to displacement. So you have d square x by dt square is equal to this. In an angular motion, in rotation, the equivalent of this expression is this. D square theta by dt square is c by I into this. Correct? Now, it is very easy. By comparison, we can write here. By comparison, we can write now. In this case, what is angular resonant frequency? Omega naught is root of k by m. So here also we can write resonant frequency omega naught is equal to root of c by I. Do you know this? In this case, resonant frequency can be proved to be this. So from this, by similarity, I am writing this. What is resonant frequency? 2 pi by 2 pi f or 2 pi by t is equal to root of c by I, or t is equal to 1 by 2 pi root I by c. Correct? So, period of a torsional pendulum. Period of a torsional pendulum is given by 2 pi into root of I by c. I is moment of inertia, c is couple this constant pi n or 4 by 2l. Okay? So, please remember this expression, you get numericals on it. This is the expression applicable for torsional oscillations. We have derived a similar formula for lab experiment to calculate Richter modulus, which you have already done it, right?